Okay, why don't we go ahead and get started? I might you can mute yourself if you're not speaking. I hear some typing in the background. Otherwise, I can just mute all the participants and have Yifeng and Alan go ahead and speak. So our first speaker today is Yifeng Hui from the San Diego Supercomputer Center. Yifeng's going to be talking about his work with the Southern California Earthquake Consortium. I see a number of other folks from the project on the line, including Phil Makeling from the University of Southern California, who's the technical lead, and also Li Wenxi, who's our new campus champion fellow, who's assigned to Yifeng and the SCEC work and has been learning about that recently. Some of the SCEC codes that Yifeng's been working on scale to really the largest machines, anywhere in the academic community, Department of Energy, NSF's Blue Waters machine. So the SCEC has really been scaling up considerably over some years, reaching kind of new heights in the realism with which they're able to model wave propagation and seismic hazards and things like that. So I look forward to hearing from Yifeng on his work, especially in the GPU area this morning. So go ahead and take it away, Yifeng.
Thanks, Nancy. And so next 20-25 minutes, I'm going to talk about the ECSS SCEC project and with the implementation of GPU for the proposed Cybershake 3.0 calculations. And first of all, some acknowledgements to my colleagues and collaborators who contributed to this project, and including ECSS folks like Jay, Amit, and Jakob, and also Matt from different sites. And this work was initially supported by TeraGrid ASTA, and including in the 3 months funding for Junzo. And also Dongju is still a collaborator. And the initial testing and the implementation was done on some GPU nodes, GPUs, and NVIDIA donated to us. And later benchmark was running on Keyland and also NCCS Titan development system. And also some thanks to Carl and of NVIDIA who for the technical support, Shuran, Karen, and BK of Ohio State, and he supported for the MWebich compiler support. And Patrick of SCEC, he prepared for the Chino Hills velocity model. And also Amit Churasia, he did the visualization for the exercise. Can you hold? So excuse me, I get somebody who come here to install cable at the wrong time. Yeah. So now, for those of you who are not familiar with, and the SCEC is an NSF consortium consisting of 64 academic institutions, including 10 international partners, I believe now, and more than 600 scientists. And that said, SCEC is not a single research group. Instead, it funds and coordinates the basic research in the earthquake science, and using Southern California as a laboratory. And there are tens of applications from SCEC in a pipeline to support their computational effort, and from community codes and to new development with some advanced features. So in coming 2013, I believe for the first time, and the computational allocation requirement will be part of SCEC IFPs for the first time. And I expect there will be an increase in terms of the requirement for SCEC, and there will be requirement for the exceeded resource and the technique support as well. So what do we see here for the computational pathway? This is a part of the SCEC CME program. It's a community model environment coordinated by Philip Magding from SCEC, and it has been a pretty successful program over the years. I think this is the 10th year anniversary. And I like this chart and it's a pretty good summary and about the work SCAC has been doing from computational aspect. So what we can start from here is that ground motion inverse problem. That's to improve the velocity models and using the 3D so waveform tomography. And the dynamic rupture modeling and is to improve the resolution of dynamic rupture simulations. And ground motion simulation is major capability simulation we will mention a little later. And the first one is the standard seismic hazard analysis. This is the major effort. The goal is to improve long-term seismic hazard analysis by replacing the empirical ground motion prediction equations with physics-based simulations. And so let's take a quick look at what we have been doing with SCAC capability simulations. The M8 simulation was done in 2010. Initial dynamic rupture simulation was done on the Kraken. And then the wave propagation simulation was moved to Jaguar using the 4x4 system and for the entire day running. And it was, I believe, it's still the largest ever earthquake simulation performed. And so this is what recent activity we have been going on, and for the Chino Hills simulation. So this is for up to 5 Hz compared to the 2 Hz we did for the M8. And also the minimum velocity is reduced from 400 to 200 meter resolution, but in a smaller scale. And with this Chino Hills, it's compared with some 2008 magnitude 5.5 Chino Hills ground motion records. And what is shows here some like the Southern California, the Q model probably is under predicts up to 5 Hz data duration in basin. So when we move to the higher frequencies, this will need to be continually tuned. But the main focus this talk is about the Cybershake. And then let's look back and what we did some years back. This is from 2009, and there was the first Cybershake 1.0 computation was done on the TAG Ranger system. There was 5.5 million CPU hours was used, and so for a typical site like USC, and the way procedure is define the rupture and the variation based on USGS and the USF 2.0. That's the Uniform California Earthquake Rupture Forecast. So then calculate the SGT, we see string grain tensors. The seismograms then is processed to obtain the peak spectral acceleration values, and they are combined with hazard curve. So in this case here, there was 5.5 million CPUs and 440 million simulations per site, because it's 7,000 ruptures and with 415 rupture variations involved. And there's also major effort here with the workflow and using the Pegasus. But we will talk more here about the string grain tensor calculation, because this is the one taking the most CPU hours.
Now, Yifeng, I wonder if you're going to say anything in the talk about how you managed 189 million jobs. That seems high.
Yeah, this is probably the so we can probably mention. I can mention briefly. This is using the Pegasus and SCAC work with USC ISI and Eva Diamant's his group her group, and so using the Pegasus basically to manage about the entire the post-processing procedure, because for each site here, in this case here, and there will be 7,000 rupture and 515 rupture variations, and that must be considered for each site, and that require approximately like 840,000 executions.
So you think, are you saying that TAC put, in some sense, Pegasus on Ranger?
Yeah, there was on Ranger, and there was also moved to the Kraken. So this is now ready on the Kraken system. That's the reason we get also support from Kraken side, and has been tested, over quite a few months this year. It's been pretty ready now, and to run a big case.
Well, yeah, it's interesting because the technology insertion service currently is evaluating, I think, Pegasus. So maybe I should tell them to get in touch with you, and maybe you can tell them who at TAC was involved and Nix, because I think that would probably make a difference to the idea that Pegasus might become generally available for Exceed users.
Mm-hmm. Yes. Okay. And so we have Jakub from the TAC, from TAC, and Matt was the one who working with SCAG on this part, and Matt left Nix, I believe, and somebody else probably will take in now. So, but I want to more focus on the Cybershake for the SGT part, string gradient tensor calculations, because this is a part of why we want to have the GPU code development. And so what the Cybershake 3.0 statewide hazard model, this is a very aggressive work plan, and for the next 1 to 2 years at SCAG, hopefully. And that will have a lot of changes based on the USF change from 2.0 to 3.0, and there will be more, including the multi-fault ruptures and also spatial temporal clustering, those kind of information. And the velocity model will be different, and also the for the 3D waveform modeling, and will be up to 1.0 Hz. So that will be 16 times more computation requirement. So counting this together will be 750 million CPU hours in total. And I think I made a mistake when I wrote my abstract. I was multi-million, and it's not. It's 750 million CPU hours required, and so probably none of the current NSS system will be able to handle with it. And so that comes to the next question: why we want to have the GPU code?
I saw over 3 billion jobs. How long are these jobs?
So it depends on, for the post-processing, it's pretty quick. Typically, it's only a few minutes, and it depends on the rupture variation case. But for the major string gradient tensor simulations, that it's for each side there will be 2 jobs, 2 simulations. So this will use probably 10,000 processor cost to use. Like in this case here, if for the Cybershake 3.0, and if we use 14,400 CPU cores, it will take 2.5 hours to run for a single run. But we will have roughly 5,000 sites. For each side of 2 runs, it's going to be 10,000 runs, and so that will take a lot of time. For if we use the traditional way, use the CPU cores. Just for the electricity, I did a rough estimate based on the Korea XK6. So this will take like $800,000 just paying for electricity. We haven't considered about the cooling here, but using GPU, there will be code will be significant reduction, and we do need a CPU as well because we need the communication between different network. And from there, I think we can save to 1/4 just for the electricity bill. So this is kind of motivation why we want to move to GPU. And a little background from the code itself. And current Cybershake using the AWP Graves code, and the plan is using AWP ODC in parallel with AWP ODC in parallel with the LRP Graves code. So because this code has been tuned over the years and within the SCAG, and has performed pretty well. So I won't go into details. And this is a code by Kim Olsen from SDSU, and a staggered grid first order, and first order in time, and second order in first order in the space, second order in time. So there's a few good features with this code, and other than wave propagation, and there's also dynamic rupture mode, and perfect match layer, and the surgeon bundling condition has been used. So for the perfect match layer, it's pretty popular bundling condition used. And for the surgeon mode, is more. This is kind of introduced the damping layer inside the computational domain. It's simple compared to the PML, but more load. There will be more computational load. And what we did in 2010, we optimized this bundling condition part so that it can actually run faster than PML. Now, for that reason, we are going to stick with the surgeon for the GPU implementation. So the other thing was noting is the memory variables, and that are used to incorporate the inelastic attenuation into the final difference. So that's to improve the accuracy of the stress relaxation schema. So these memory variables, however, it's require larger computational storage requirement. What Steve Day introduced in 1998 is a method. So in this method, the memory variables are coarse-grained. So that's distributed in such a way that a single relaxation time is represented in each node point. So for the 3D case, we need only one memory variable per stress component now, and compared to 8 memory variable before. So the code scales well on the CPU code scales well, and that is showing the strong scaling and the weak scaling. We even see the superlinear speed up with the strong scaling because of the effective cache use, as many of you know. And for the computational kernel part, it's pretty straightforward. It's for each time in the time loop here, each iteration. So you update the velocity by the stress, and then update the stress by velocity. So there's 21 arrays involved, and depends on the bundling condition. For the PML, we need a few more variables. So for the tensor computation, it's very typical. You get a low computational intensity, and for our case here, it's memory access is a major bottleneck. And what you see here, we see the low flops to bytes ratio, and also the low flops memory access ratio. For that reason, the memory access optimization is important with this code. So now we look into the decomposition, and what I show here is decomposition with the method we used for the CPU side. This is a little different from the decomposition we used for the CPU code. So for the CPU code, you get enough memory. It's very straightforward to do the 3D decomposition. But with the GPU, NVIDIA GPUs, and the way we do is have the 2D decomposition on the CPU side, and put the 1D into GPU. This is a very typical standard method that people use. So for the GPU, we from the GPU side, and we kind of have again and second round of decomposition, and we picked the Y and the Z direction. So the reason is because CUDA is extended language of C and C++. So memory storage and for the 3D arrays and typically will be faster in the Z direction, and the slow will be in the X direction. So if so to do this way, we can kind of obtain a better cache hit rate, so that we can allow all threads in the same warp to access data along the fast Z direction instead of the slow X axis. So the entire threads will be calculated the NX and in a given the 2D from Y and Z. So this is the approach we use. And the single GPU optimization, this is the part we spend a lot of time working on, and its major restructurings were made. And we kind of completely rewrote the code from scratch and from Fortran change it to C, and then start edit the CUDA. And so then, the later stage we edit the MPI. So other than the 2D decomposition we just mentioned, and in the YC direction only, and there's a few other features we used. For example, the texture and the constant memory. And this is a texture constant memory in the GPU device has its own cache. So in the texture memory case, we use 6 3D constant variables, and for the scalar constant 3 and scalar constant we put into the constant memory. So that's to save the register use. So all other 15 arrays we still put into stored in the global memory, because these values will be updated during the iteration. So the global memory coalesced here, and this is probably most important touch with the single GPU optimization. And the global memory access on the GPU takes about 100 times as many instructions as in the local memory access. So if you have coalesced the global memory access, you will save like 100 times of instruction per thread. And so to do it, we use stride 1. So every thread access memory within the same 128 bytes aligned memory segment. So hardware can coalesce into one section, a transaction. So the purpose is to load the needed memory in as few memory transactions as possible. And then also with the register pipeline register copy, I will mention it later. And the other things with the shared memory and optimization part. And in the GPU firming and provide, there's two different kind of configurations. Either you can use 48 kilobytes L1 cache and 16 kilobytes shared memory for L1, or you can other way. What we choose here, we choose L1 over shared in the code. So the reason is because we had two layer growth cells that are typically bottleneck for the high efficiency when you fetch data to the shared memory. And so I will show a little bit about the register optimization part.
You have just about 5 minutes, do you think?
Okay. So I got to run a little quicker, and each thread has its own registers, and the private register will be fastest on the cheapest GPU memory. And when we did the 3D decomposition inside the GPU, the 2D is at YZ direction goes to the L1 local shared memory, and the other from X direction we use registers. We use 4 registers per thread to store the data. So the way here is we put a pipeline and shift it, so that each time you need only access global memory once with one single variable. So that can save 75% of the global memory access in X direction. And flops optimization, that's what you see here. Is since we touched lots of tunings, and you can see from very few gigaflops moved up to 100, up to close to 150 gigaflops. This is for the single GPU. This is pretty good for tensor computation. And we get how much? Probably 12% of the peak, and 10 or 11% peak.
Yifeng, what was the baseline on?
The baseline here is talk about without any. So like if we use the regular without the tuning, we don't use the global memory coalesce. We don't use the register optimization. We don't use the L1 cache.
Okay, but the baseline was on the GPU?
Yeah, it is on GPU, yes.
Okay, thank you.
And this is now for the multi-GPU workload. And I will go a little quicker and go to next slide about overlapping procedure. And this is a major effort done, and it's unpublished now. We are writing paper on it. And this is two approach we did here. And the first is about we want to keep the workload as much as possible in the GPU side. And the original was there was updated communication 3 times within the same time step. And we made changes and to have only one communication at the end. The second is we use overlapping communication and execution through the asynchronous memory copy. So and also using the multi-CUDA data streaming part. So from there, what we see, the code perform extremely well, and this is testing on the Keyland and also the Titan system. What you can see on the Titan up to the test system up to 900 some GPUs, and we get 100% of the overlap. So you get the perfect speed up because communication time you will not see here. This is for the verification, and the CPU code has been tested pretty well, and I will not get time to show the movie. Amit produced a few months back, but this verification is compared with two code. At the beginning, we had some issue because of the position and between CPU GPU is a little different, but we make some changes using the intrinsic function, and so that we get the same results now. This is a comparison of the current LRPODC code with Rob Graves' code, and that's for the CPU code for the string green tensors calculation. And this verification test is still in the process. It's pretty long process because there's two codes has quite some difference in the local coordinate system, and also with the free surface like handling is different. So that's the reason we take some time to do the verification. And once this is ready, and then we will move up for the production run, and also we will start to add the string gradient tensors calculation to the GPU code. At this moment, the GPU code is only running for the velocity outputs, and the string gradient tensor has not been implemented. And also, there's still a little work with I/O, but the GPU code is ready to have the production run. So the long-term goal is to develop a Cybershake model that can simulate the information during earthquake cascade for the operation forecast, and also for the early warning. So to the last, just mention as Nancy talked earlier, we get the Professor Liwen. She working with me. I'm really glad working with Liwen. And for the next few months, we will work on the GPU optimization as well on the Cybershake workflow optimization part with Liwen. So that's my talk. Apologize for taking too long time.
No, Yifeng, thank you very much. That was an excellent talk. It could have easily fit into an hour. There was so much to ask about. We had a lot of questions during your talk. Is there anyone on the call who would like to ask one question to Yifeng now? Okay, great. The slides will be posted on the symposium website, and there's also contact information there for both Yifeng and for Alan. So if you want to ask some questions offline, there's plenty of time to do that. So very, very impressive talk. So you're looking at your end goal is operational forecasting. So so during an event that quickly, did I understand that correctly?
Yeah, this is going to be actually what we want to do. I think it's Tom Jordan and from SCAG director. He want to do, and he want to prepare production capability, and for the short-term forecast. So there are procedures. You compute the probability gain associated with recent seismicity and activity. And then you apply probability gain to the Cybershake rupture with a high percentage near the recent events. And then you recompute the Cybershake ground motion probability for shorter interval in the following events. So that's for 1 day probability. So this is going to be, it's very interesting. It's a short-term forecast.
Yeah, it sounds like an exciting project to be working on.